Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. This week, I wanted to revisit a subject that keeps coming up in comments. When you start to design your own spaceships, what materials should you use in the hull? Let's review the design considerations for re-entry and radiation shielding. Hull and shielding basics. You've been selected to be the chief engineer of a new spaceship design. You decide to start with the choice of hull and shielding. The material with which to build the hull of a spaceship must be carefully considered. There are a huge variety of material choices, each with its own strengths and weaknesses. The first question you must ask is, where will my spaceship be built? If it is going to be built and launched from Earth, it will have to have a very strong propulsion system to get through Earth's thick atmosphere and out of Earth's powerful gravity well. Gravity on Earth is 9.8 meters per second squared, giving a force of 9.8 newtons per kilogram. The escape velocity of Earth is 11.12 kilometers per second. If it is going to be built in orbit and used only for in-space operations, then it can consist mainly of inflatable habitats with metal trusses for support. It does not need to be aerodynamic, as it could never survive flight through an atmosphere. You would have atmospheric-capable lifeboats on board to evacuate the crew in case of failure to maintain orbit or a massive fire or some other disaster. If it is going to be built and launched from the moon, it will not have to contend with any significant atmosphere, so it does not have to be aerodynamic, and it will only have to fight a gravitational acceleration of 1.33 meters per second squared, giving a force of only 1.33 newtons per kilogram, about 1/6 of that on Earth. The same propulsion system used on Earth could loft a much bigger ship, all considered about 10 times as big. Also, the surface of the moon is mostly titanium and aluminum. Titanium is lighter, 4.54 kilograms per liter versus 7.87 kilograms per liter for steel, and stronger. A SpaceX Starship made of titanium alloy on the moon could be much better than one made from steel on Earth, and more heat resistant, as titanium alloy can take temperatures of 1725 Celsius versus 1500 Celsius for steel, and only 660 Celsius for aluminum. If your ship plans to re-enter an atmosphere like Earth or Mars and be reusable, it will have to be steel or titanium. If it is constructed in lunar orbit with material sent up from the moon, you could build a truly massive ship, as a magnetic catapult system could send huge amounts of material from the moon to the orbital construction facility. Let us look first at leaving Earth. To decide the material to use for your rocket to survive its climb through the Earth's thick atmosphere and strong gravity, you must first consider the size of your rocket. We will call the rocket the lifting part of your ship, and the spaceship is the functional part that operates in space. If your rocket is very small and you are sending up a small satellite or space probe, you could use carbon fiber. It is very light and strong and durable for most operations. As your rocket and ship get bigger, the carbon fiber becomes less cost-effective, as it is very expensive, and as you increase the radius of a rocket, it takes more material to provide sufficient strength and durability, as the wall gets thicker to withstand tension and external and internal forces. A 1 centimeter square, 5 millimeter thick piece of aluminum is very hard to bend. A 1 centimeter wide, 1 meter long, 5 millimeter thick piece of aluminum is very easy to bend. Small rockets like the Electron rocket by Rocket Lab work great for low mass launches and even survive re-entry to be used again. This is an essential consideration for sustainable space exploration. Non-reusable rockets are a dead end. A larger rocket like the Falcon 9 is usually made of an aluminum lithium alloy, which provides greater strength at a lighter weight. These alloys are about 6% lithium. Lithium is the least dense metal possible until we can make metallic hydrogen, with a density of 0.53 kilograms per liter. Aluminum is 2.7 kilograms per liter. Magnesium is also used in some alloys with a density of 1.74 kilograms per liter. It is also possible to use a very thin layer of aluminum alloy for the tanks and then wrap them in carbon fiber. This becomes a carbon overwrapped pressure vessel because it can withstand extreme pressures. It is hard to make a woven material hold compressed gas, but with this technique you get the strength of carbon fiber around the impermeability of a solid metal structure. For a massive rocket, it turns out that aluminum alloy or carbon fiber may not be the best choice. And if you plan to have re-entry with your ship, these would not survive anyway. Advanced stainless steels, iron with a small amount of chromium and sometimes other metals added, turns out to be a good choice for these applications. Now let us look at the shielding ability of these materials. The greatest danger in space travel is galactic radiation. If you are unfamiliar with the types of radiation, please review the Space Survival Training Virtual titled Understanding Radiation in Space. Galactic radiation is generated by high-energy events outside our solar system or galaxy that generate large atomic nuclei traveling at near light speed. This radiation is very damaging to the human body. To safely travel in space, it must be shielded against. The best materials for shielding against cosmic radiation are the lightest elements. Think of a hurricane blowing through a forest. The older, stronger, but more massive trees are shattered, but the smaller, lighter trees flex with the force and absorb it without breaking. Spacecraft materials work the same way. When a high-speed cosmic particle, or Z-particle as they are called for having an atomic number of 2 or above, hits a massive atom, it can split pieces off that atom, sending out dangerous neutrons and other radiation. When the high-speed Z-particle hits the nucleus of a lighter element, the nucleus rebounds and absorbs the impact, with much less secondary radiation being produced. Materials that work well to absorb radiation include liquid hydrogen, water, liquid methane, plastics, and light metals like lithium. If you are building a spacecraft for more than a few days of space operations and humans are going to be on board, the choice of shielding becomes critical. The Apollo astronauts did not have much shielding. They spent about 7 days on their way to the moon, 2 days there and 7 days back. Parts of their ship were made of aluminum as thin as a soda can. This allowed the galactic and even some of the solar radiation to penetrate the hull and their bodies. They all reported seeing bright flashes as the particles penetrated their eyes and brains, causing breaking or secondary radiation, including photons, to be produced. Each of these hits is like being shot by a microscopic bullet. 1 or 2 probably would not do much, but thousands per second over time will cause a lot of damage. There is significant evidence indicating that all the Apollo astronauts are suffering from health effects of this radiation. Anywhere outside the Earth's protective magnetic shield, which means anywhere above low Earth orbit, will have this radiation danger. It would be best to consider heavy shielding for any colony ships to the Moon or Mars, and for any habitats placed on them. It is critical for deep space exploration ships to have this shielding. While astronauts over the age of 45 who do not plan to have any more children can survive extended periods of high radiation doses fairly well, this is not what you will be sending to a colony. You will be sending young people, eventually even children, and shielding must be the first consideration. To provide adequate shielding, you could launch a spaceship from the Earth in a large reusable steel rocket, like the SpaceX Starship. You would then be able to release a 100-ton spaceship made of lighter elements like aluminum with a high lithium content. This spaceship could have inflatable habitat modules like those that were designed by Bigelow Aerospace. These habitats in your main ship will need water shielding also, about 1 meter of it, to bring it down to Earth normal radiation levels. One solution is to have given the ship liquid methane or hydrogen fuel tanks with liquid oxygen tanks also. The habitation area is inside these tanks, insulated from the cold. Boil off from the tanks combines with pumped fuel and oxidizer and put through a methane or oxygen fuel cell. These can be about 90% efficient in converting the chemical energy into electricity. The electricity produced by the fuel cell would be used to power an ion drive, either a Hall thruster or Vasamer or some other ion propulsion system. If you are unfamiliar with these designs, see the virtual on propulsion. The fuel cell could produce pure water if you use only hydrogen or water, and carbon dioxide if you use methane. The water can be pumped into the inflatable habitats and into a double hull around the metal parts of the ship to provide shielding. The carbon dioxide can be turned into dry ice and used for shielding also. As the ship travels, it will produce more and more shielding until it has enough to safely shield colonists. The ion engines would provide a faster trip with less total exposure. The habitats could rotate, allowing for artificial gravity to maintain muscle, bone, and cardiovascular health during the flight. If the first trip to Mars has a crew of older astronauts, they can use landing craft to get started on Mars base infrastructure, while the ship autonomously returns to Earth orbit. This concept is called the Aldrin Cycler in honor of Buzz Aldrin, who developed a workable concept of this technique. By the time the ship is back in Earth orbit, it would have sufficient shielding for regular passengers. A SpaceX Starship could then bring them into orbit for docking and transfer. One refueling flight from a lunar outpost or from a Starship tanker could then refuel the ship for its next trip to Mars. Solar power would do the rest. Every flight thereafter would be shielded. Additional cyclers could be placed in this orbit and shielded. A long ride in a shielded ship is not a danger to the colonists. Electric ion propulsion could maintain the orbit and allow for course corrections. This is the only feasible concept to colonize Mars. Planning to send young men and women in unshielded steel ships is not reasonable. Plastics are also exceptionally good at stopping radiation safely. Consider making the interior of your craft out of durable, temperature-resistant plastic if you can. If you are making a ship on the moon, you could just make it bigger with a double hull and water shielding. One of the other significant dangers in space is micro-meteoroids. These are small rocks flying through space that can impact the ship. In orbit, flecks of paint hitting the space shuttle windows created large craters in the armored glass. It would be best to use aluminum oxide glass, as this is stronger than silicon dioxide glass. Using cameras and screens and limiting windows to only where absolutely necessary will be safer. The impact from these meteoroids must be safely absorbed by the hull of the ship. Kevlar and carbon fiber materials are extraordinarily strong and best for this. Consider fabric shielding made from these or similar materials. Carbon nanotubes will be great when they are available in sufficient quantities. Until then, use advanced ballistic cloth to protect from this threat. In summary, the first layer of any true spaceship designed for long-term operations will need to be made from a material that can resist micrometeoroid impacts, thick metal or ballistic fabrics. You can use multiple layers of fabric and plastics for an inflatable design, or use a thick metal with water or plastic shielding to stop the secondary radiation. The interior of your ship should be high-strength plastic for further mass reduction and radiation protection. Consider inflatable interiors for metal ships, as it would be safer for humans impacting the walls during maneuvering or just getting around the ship. Consider fabric ladder-like handholds and 2 tracks to allow brachiation in zero gravity to prevent collisions with the bulkhead or other people. This technical training manual covered the materials necessary for building small, medium, and large rockets, and the hull materials and engineering requirements of large spaceships designed for continuous operations in space. These additional lessons explain steel alloys, like those used on the Starship, aluminum alloys, used in almost everything else, and this one covers composite materials, like those used by Rocket Lab in the Electron rocket. If you'll forgive me saying millimeters instead of micrometers at one point. Thanks for listening. Please don't forget to like and subscribe, and stay safe. At Astra Pro Terra.